Okay, let's dive right into this. Welcome to The Explainer. Today, we're tackling a concept that honestly is going to feel completely backward at first glance. We usually think of materials as being perfectly solid, pristine, and flawlessly ordered on a microscopic level, right? But here is the wild, counterintuitive premise of material science. Perfect solids absolutely do not exist. And honestly, we really wouldn't want them to anyway. So that brings us to the big question. What actually makes an imperfect solid so perfect? I want you to completely rethink the word defect. Normally, if you buy something and it has a defect, well, it's broken. You return it. But in crystalline materials, a defect is basically the exact opposite of a mistake. These microscopic flaws, we're talking missing or extra atoms, they're actually intentionally engineered features. They're the secret sauce that gives materials their strength, their everyday usefulness, and their incredible chemical properties. Now, what's really interesting about what we're looking at here is that dark void right in the middle. You're seeing a super high-resolution atomic defect, literally a scanning probe micrograph showing a single solitary missing atom on a silicon surface. It looks like a glitch, right? But these exact types of microscopic flaws are literal world savers. Take your car's catalytic converter, for instance. The metals inside are absolutely packed with surface defects exactly like this one. When dangerous polluting gases from the engine exhaust hit that metal, they actually attach themselves right to those specific defect sites. And while they're trapped there, they undergo a chemical reaction that converts them into safe, non-polluting substances before they even leave the tailpipe. No flaw, no reaction. It's that simple. Section 1. The power of imperfection. Let's really pin down what we mean when we talk about these powerful little flaws. By definition, a crystalline defect is basically just a lattice irregularity. We're talking about a disruption on an incredibly tiny scale, literally on the order of an atomic diameter. But why are they everywhere? Well, it actually comes down to a fundamental rule of thermodynamics. Nature absolutely loves randomness, or entropy, way more than perfect, flawless order. So even if we tried our hardest, it is thermodynamically impossible to create a crystalline solid that is 100% free of these irregularities. The material actually wants to be imperfect. Moving on to Section 2. Meet the point defects. Let's look at the absolute simplest category of these irregularities. We're looking at two different atomic scenarios here. On one side, we have what's called a vacancy. That's exactly what it sounds like, an empty space in the atomic lattice where an atom normally belongs, but it's just mysteriously missing. On the other side, you've got a self-interstitial. This happens when an atom from the crystal itself gets tightly squeezed into a tiny, naturally occurring void space between the other atoms. But look at how warped and distorted the surrounding rows of atoms get. That squeezed atom is substantially larger than the tiny void it's hiding in, so it pushes everything else out of whack. Because of that extreme crowding, self-interstitials are highly improbable and incredibly rare compared to those simple vacancies. Section 3. Calculating atomic vacancies. Since these missing atoms are the most common natural defect, let's put some math to the visuals. Try to guess just how many missing atoms might exist in an everyday piece of metal. Let's say a block of pure copper heated up to 1,000 degrees Celsius. Did you guess this absolute monster of a number? 22 septillion. That is 2.2 times 10 to the 25th power. That staggering figure is the equilibrium amount of vacancies in just one single cubic meter of copper at 1,000 degrees Celsius. To put that into perspective, just below the melting point, roughly 1 out of every 10,000 atomic sites in a metal is completely empty. It's like a giant stadium where thousands of seats are just randomly, totally vacant. The mathematical scale of this imperfection is absolutely mind-blowing. Now, how do we get that massive number? We use a specific equation with a few key variables. We've got N for the total number of atomic sites, QV for the energy needed to actually form a vacancy, K is Boltzmann's constant, and T is our absolute temperature. But here's the absolute crucial takeaway from all this math. It's all about that T variable. The number of vacancies has an exponential dependence on temperature. Meaning as the temperature goes up, the number of vacant atomic sites doesn't just increase, it literally explodes. Section 4. Intentional impurities, also known as solid solutions. So the crucial point we're getting to is that while nature gives us natural defects like vacancies, as material scientists, we don't just sit back and accept them. We actually intentionally introduce our own flaws. We call this alloying. To wrap your head around how we force foreign atoms into a pure metal, think about a super common liquid analogy. If you mix water and alcohol, they completely dissolve into each other, right? They create a perfectly homogeneous liquid solution. Well, solid metals can do the exact same thing. When we add an impurity, we're making a solid solution. The element that does the heavy lifting, the one with the greatest amount, is our solvent or host atom. And that tiny bit of minor element we sprinkle in, that's the solute. Those impurity atoms just disperse randomly and uniformly throughout the whole solid structure. A brilliant real-world example of this secret recipe is sterling silver. See, pure silver is beautifully corrosion-resistant, but it's way, way too soft to actually use for much of anything on its own. So what do? We intentionally introduce a defect. By mixing just 7.5% copper solute atoms into the 92.5% silver solvent, the entire solid solution fundamentally changes. That copper acts as an impurity point defect, and it significantly boosts the mechanical strength of the material. Boom, you get highly durable sterling silver, and you don't even sacrifice that beautiful corrosion resistance. It's a total win-win. Section 5. The Hume-Rothery rules. Now, you might be wondering, how on earth do scientists know if an impurity will actually mix smoothly without just totally destroying the crystal structure? Well, they have to consult the atomic rulebook. Think of these 4 rules as the absolute, no-nonsense bouncer at the atomic club. These are the Hume-Rothery rules, and they strictly dictate whether atoms are allowed to safely swap places to form what we call a substitutional solid solution. Rule 1. The size difference between the atoms has to be less than 15%. Rule 2. They need matching crystal structures. Rule 3. Their electronegativities need to be pretty similar so they don't accidentally freak out and form an entirely new chemical compound. And finally, Rule 4. Their valences need to match up nicely. If an atom meets all these strict VIP conditions, kind of like copper and nickel do, they can hang out and mix endlessly in any proportion. But wait, what if an atom totally fails to meet the bouncer's rules? Look at that tiny atom right there. Instead of substituting for a host atom, it's just sneaking right past and squeezing directly into the empty spaces, the voids, between the host atoms. We call this an interstitial solid solution. Carbon atoms actually do this inside of iron to create incredibly strong steel alloys. But because metallic atoms are already packed together so tightly, these interstitial intruder atoms have to be exceedingly small, and even then, they cause a lot of strain on the lattice. Because of that, their maximum concentration is strictly capped at under 10%. With carbon and iron, for example, the absolute max concentration you can get is only about 2%. And this brilliantly illustrates exactly where these tiny intruder atoms are actually hiding. What you're seeing are the 2 specific types of voids in the crystal lattice. We have tetrahedral sites, where an atom is surrounded by 4 host atoms forming a tiny pyramid, and then we have octahedral sites, where an impurity atom is surrounded by 6 hosts. Depending on whether the metal structure is face-centered cubic or body-centered cubic, these tiny, highly specific pockets dictate exactly how and where an impurity can squeeze in and completely alter the physical fabric of the material. It's like a giant 3D atomic puzzle. So, what does this all mean? Well, it brings us to a really fascinating final thought. We've seen how billions of random vacancies naturally occur, and how we intentionally force foreign atoms into the microscopic voids of a metal lattice to fundamentally change how it behaves. The entire modern world around us is literally built on these deliberate imperfections. But it begs a pretty critical question. If perfect solids just don't exist, how do scientists perfectly measure and communicate the microscopic recipes they're creating? Well, answering that requires a deep dive into the complex math of composition, calculating exact weight percentages versus atom percentages, which is a precision story we're going to save for our next explainer. Thanks so much for joining me on this journey into the atomic world.